So now we're going to talk about implicit derivatives. And this would be trying to take the derivative with respect to x, or a variable that's not actually in the equation. So if an equation isn't explicitly defined, it's not solved just for x, then we say that that equation is implied by others or other variables, so implicitly defined. So what does that mean? If we can't solve for y, or if the equation isn't all in terms of one single variable, then we just have to keep in mind the chain rule. Because remember, we said if we have some f of u, and u is something in terms of x or something like that, then the derivative f prime of u is the derivative of f with respect to u multiplied by the derivative of u. And I usually write u prime right here, but let's write du dx. So we're going to keep that chain rule in mind. When you're taking a derivative, if the variables in the equation match what you're taking the derivative with respect to, then you don't have to worry about this. So this derivative is just 3x squared. If the derivative that you're taking is with respect to x, but your equation is in terms of y, you're going to take the derivative of y to the third. This is like the f prime of u part. So that's 3y squared. But then chain rule, you have to multiply it by the derivative of y with respect to x. And we just write that as dy dx. So it is multiplied by whatever that derivative is. For this one, we have two terms. The derivative of x with respect to x is 1, plus the derivative of 3y with respect to x is 3, and then chain rule, dy dx. For part D, I've got a product rule here. So the derivative is the first function times derivative of the second, 2y, and then a dy dx, plus the second function, derivative of the first, derivative of x with respect to x is just 1. And I might clean this up a bit, like 2xy times dy dx plus y squared. What we're going to be doing with this eventually is solving for dy dx. So this is, think of it as its own little variable. This one says dy dt, derivative with respect to t. That usually means time. So that doesn't match either of our variables. So when we do our product rule, it's the first function times the derivative of the second. So this isn't going to be dy dx, it's going to be dy dt, plus the second function times the derivative of the first. Derivative of x is 1 times dx dt. And I can clean that up, make it like 4xy to the third dy dt plus y to the fourth dx dt. So some kind of like a checklist here, some guidelines for implicit differentiation. If you're working on an equation like we're about to do, differentiate both sides with respect to x. That would look like this. Differentiate with respect to x of this side, and I'm going to do the same thing to this side. And then once you take your derivatives and you have all your little dy dx's and everything else, collect all terms involving dy dx on the left side of the equation, then we'll move everything to the right. And that will allow us to factor out a dy dx and then solve for dy dx. We've done something similar if you've had variables where x's and y's are being multiplied and you're supposed to solve for y. So this might look familiar once you start doing it. So first step, differentiate with respect to x on both sides. Now I don't have room to squeeze in the d dx, so I'm going to just do it on the right side there. It's with respect to x. So anytime you have a y, you need to make sure after that term that you multiply by dy dx. So the derivative of y cubed is 3y squared dy dx. Plus the derivative of y squared is 2y dy dx. Minus 5 dy dx. Minus 2x. I don't need a dy dx because this is the derivative of x squared with respect to x. And that equals the derivative of a constant is 0. And again, that's with respect to x, so I don't need a dy dx there because it's just 0. So we want to keep all of our dy dx terms on the same side. That means that I should just add the 2x to the other side. I'm going to kind of combine steps 2 and 3 on this problem, and go ahead and factor out a dy dx. That would leave you with 3y squared plus 2y minus 5 equals, I added 2x over to the other side. And step 4 is solve for dy dx. You can divide by this entire quantity. Dy dx equals 2x divided by 3y squared plus 2y minus 5. This is still a formula for the slope of a line tangent to the curve, y equals whatever, tangent to the function, at any given point. And since we have x's and y's in here, when we have an ordered pair, we need both the x and the y to be able to plug into this to get the slope. So find the equation of the tangent line at this point. So we have the point, we need the slope. That would be dy dx evaluated at 1, -3 into this equation. So that's 2 times 1 over 3 times -3 squared is 9, plus 2 times -3 minus 5. That's 2 over, let's see, 27 minus 6 minus 5. So 2 over 16, 27 minus 11, which is 1/8. So find the equation of the tangent line. It would be in point slope form. Y plus 3 equals 1/8 x minus 1. Find the x values where the tangent line is horizontal. The tangent line will be horizontal when dy dx equals 0. When you're doing free response questions, it's a good idea. This is kind of like explaining your work. So your first step is to say dy dx should be 0. Set your dy, excuse me, dx equation equal to 0. So 2x 3y squared plus y minus 5 equals 0. Now remember, excuse me, a rational equation is equal to 0 when just the numerator is equal to 0. So 2x equals 0 when x equals 0. And it says just find the x values, not the ordered pairs. So I'm finished at that point. Example 2, find dy dx. So again, let's take the derivative of both sides. So I get 3x squared plus derivative of sine is cosine y, and then dy dx equals, we need a product rule here. So you could do this 2 ways. Keep the 3 out and distribute it through your product rule at the end, or I just like to lump it together. 3x is my first function and y squared is my second function. I think that's easier. So 3x times 2y dy dx plus the second function times derivative of the first. It's probably a good idea to clean this up a little bit before we start collecting things. So let's make this 6xy dy dx plus 3y squared. So we want our dy dx's on the left. It doesn't have to be the left side, by the way. It's just that's usually easier to look at. Then on the right side, we should still have 3y squared, and we're going to subtract 3x squared from that. Now, if you want to do this in one step, I think that's okay too. You factored out dy dx, what would you have divided to the other side? So you have 3y squared minus 3x squared over, this would have been cosine y minus 6xy. And again, this is still a formula for the slope of a line tangent to whatever the function is at any given point, and you would have to have the entire point xy to be able to find the value of that slope. On example 3, same thing. We're going to have to use a little chain rule here and product rule. Okay, so the derivative with respect to x here. So first, we're going to take the derivative of 3 times something squared. So that is going to be 6 times the thing to the first power. And then we're going to take the derivative of the inner function. So the derivative of that is 2x plus 2y dy dx. And then that's equal to, on this side, we have a product rule. My first function is 100x, my second one is y. So 100x, derivative of y is 1 dy dx, plus y, derivative of 100x is 100. Now, I need my dy dx terms together, so I do need to distribute this through. So I have 6x squared plus 6y squared. I'm going to multiply that through this binomial. So I'm going to get 12x to the third plus 12x squared y dy dx plus 12xy squared plus 12y to the third dy dx equals 100x dy dx plus 100y. Let's get our dy dx's on the same side. And our non-dy dx's on the right side. So we had 100y, subtract 12x to the third, subtract 12xy squared. Factor out a dy dx and go ahead and divide by what you factored out. Now, I know there is a GCF. I can divide, a 4, I believe, 4 out of both sides. In interest of time here, because I don't want my video to get cut off. Just, I know I can do that, and I'd be looking for that answer if I needed to, or if I needed to work with it further. Okay, this next example. We have 2 product rules going on. This term and this term both need product rule. So when you take the derivative with respect to x of both sides, we have first function x squared times derivative of the second plus second times derivative of the first, and then plus first function times derivative of the second, plus second function times derivative of the first. And then on the right side, derivative of a constant is 0. So I'm going to get my dy dx's together. And subtract non-dy dx's to the other side. So minus 2xy minus y squared. And when I factor out a dy dx and divide, I have got negative 2xy minus y squared over x squared plus 2xy. Again, you could maybe factor out a negative y from the numerator. It's not going to help you cancel anything, but you might need to look for equivalent answers if it's multiple choice. What if I want to find a second derivative? So start the same way. Find the first derivative. Okay, so derivative of a constant is 0. And then I like to think of this as negative x is my first function and y is my second, so that I don't have to worry about distributing a negative. So the first is negative x times the derivative of y plus y times the derivative of negative x. And then that would equal derivative of x is 1 minus derivative of y. We still need to solve for dy dx. So let's see. So it'd be plus dy dx equals 1, and then this is negative y, so plus y on this side. So dy dx is going to equal 1 plus y, and then when you factor it out of the side, negative x plus 1, or 1 minus x. This is the first derivative. Now the second derivative is taking the derivative again with respect to x of both sides. And we're going to need quotient rule for this one. So the second derivative of y with respect to x is low d high, derivative of 1 plus y is dy dt, or dy dx, minus high d low, derivative of 1 minus x is negative 1, over low. Now, we don't want to have dy dx in our answer, but remember, we know what dy dx is equal to. So I have 1 minus x times, what is dy dx? It's 1 plus y over 1 minus x. And then let's make this plus 1 plus y. And some nice things happen in this one. The 1 minus x's cancel. You've got 1 plus y plus 1 plus y. So you've got 2 plus 2y over 1 minus x squared. That is our second derivative. So you know your second derivative formula is finished as long as you don't have dy dx in it still. So same thing for this last one. Let's take the first derivative of both sides. Derivative of 9 equals 0. Let's solve for dy dx. There's no factoring to be done. I would have subtracted 2x and divided by 32y. So clean that up. That's negative x over 16y. I have to do quotient rule to take the second derivative. Second derivative of y with respect to x. It's quotient rule again. So low d high minus high, minus high minus negative x d low over low. My brain can't think of 16 squared at the moment. There we go, 256. Since it was low, I was just going ahead and squaring it. This would be negative 16y plus 16x. What is dy dx? It's negative x over 16y. That cleans up a bit. Negative 16y plus the 16's cancel, so I shouldn't say plus, I should say minus x squared over y. Now we don't want to leave our answer as a complex fraction, so a quick fix for that is to multiply by y over y. So final answer for the second derivative is negative 16y squared minus x squared over 256 y to the third. And again, we could factor the numerator, but I'm not going to bother doing that unless I'm actually solving or trying to find my answer that's not showing up, but there's an equivalent answer somewhere in multiple choice. So work on this practice and then check my PDF of my answer key. And then we can talk about this practice tomorrow in class.